Every subject has its own famous categorization schema. In biology, it's the tree of life. In chemistry, it's the periodic table. In physics, perhaps it's the Standard Model. Particle physics may seem abstract, but you may have heard of some of these particles before. The up and down quarks are found inside each atom's nucleus, which are held together by gluons. How do we see? Our eyes can detect light, and the particle that is responsible for this would be the photon. But were it not for the electrons, the atoms would not bond with other atoms to form the molecules that are so essential to life. In our daily experience, we feel that most objects have mass. It is most appropriate, then, that the electron and up and down quarks have mass too. Particles get their rest mass from the Higgs boson and its corresponding field. In practice, however, it's just the electron, the up and down quarks, and the gluon that can be found within the atoms which make up the molecules that make up you. But these aren't the only particles. What are the stories behind the others? The up and down quarks are the first generation of quarks because they are the most stable. Higher energy quarks have shorter lifetimes and decay faster. All 6 of these quarks display a property called color confinement. Side note, it's not actually color. It behaves similarly to charge, but instead of an electric force, it's another kind of force. This means you can never observe a single quark by itself. Any energy that you try to put into creating another one will lead to the creation of more quarks instead. This means that you can never observe a single quark by itself. It has to be found inside another larger particle, like a proton. These quarks are the children of the strong force, which binds them together. Specifically, one form of the strong force, the color force, is what allows gluons to keep the quarks together within a proton or neutron. But despite being a very strong force, not all particles care for it. The electron is part of the first generation of leptons. Being negatively charged but colorless, it is only affected by the electromagnetic and weak forces. The 2 heavier particles in this category are the muon and the tauon. These particles actually provide evidence for time dilation. Muons and tauons are produced in our atmosphere by cosmic ray collisions from outer space, but we predict that their lifetimes are so short that we could never detect them from the ground. They would decay into other particles. But we can. Since they move at near light speeds, this short of a time for them is much longer for us. Neutrinos are elusive particles. Although they are leptons, they are uncharged and thus are unaffected by all forces except the weak force. That's another force, and it is, as the name suggests, weaker than the strong force. There are many conservation laws in physics, which is a fancy way of saying nothing is free. Momentum is conserved, energy is conserved, and in this case, something called lepton number. When heavy radioactive atoms like uranium-239 decay, a neutron inside the nucleus turns into a proton, thanks to the weak force, and an electron is ejected. But an electron is a lepton, yet we started out with 0 leptons. Because nature wants to conserve the lepton number, we need an anti-lepton to be formed, specifically the electron antineutrino. Neutrinos are weird in that because they interact with only the weak force, they can pass through pretty much anything, unaffected. They also have incredibly small masses and travel close to the speed of light, but we know that their masses cannot be 0. Analogous to the electron, muon, and tau, we named these 3 generations the electron, muon, and tau neutrinos. Due to a phenomenon called neutrino oscillation, each neutrino can oscillate into another. An unsolved question right now is whether or not neutrinos are their own antiparticles. That is, are they Majorana particles? Analogous to the gluon for the strong force, the weak force also has its force carriers, the W+, W-, and Z0 bosons. Within radioactive decay, the weak force that turns a neutron into a proton is really turning a down quark into an up quark in a W- boson. In fact, this W- boson is what later decays into an electron and an electron antineutrino. Are we done? Yes, with the Standard Model, but there are many more possibilities when we start combining them. Many more composite particles exist. The bits of the universe that we are studying are getting smaller and smaller, and at this point some properties of these particles can't be known at the same time, thanks to the Heisenberg uncertainty principle. But there are many more areas of particle physics in which we are still eagerly searching for answers. What's next? Supersymmetry? Dark matter? The expansion of the universe? These questions are being pondered today, but now you at least know what we know now, and maybe you can help us figure out what there is to come.